integer partitions, or partitions of an integer. So if we have some integer n, and we're gonna just work with natural numbers. They're called partitions of integers, but they're typically in particular, they're particularly natural numbers. So for some natural number n, we want to know p of n, which is the number of multisets of natural numbers summing to n. All right, so let's do an example. Let's look at all of the ways to partition the number 4. So I can write 4 as 4. I could write 4 as 3 plus 1. I could write 4 as 2 plus 2. I could write 4 as 2 plus 1 plus 1. And I could write 4 as 1 plus 1 plus 1 plus 1. By the way, we typically write these in decreasing order. So now I want to look at this set of partitions of 4. I guess I should say this is an example. Let's let n equal 4. And I want to see if there's some interesting way we can generate these by looking at generating functions. Well, you'll recall that 1 over x minus, 1 minus x generates all 1s. 1 over 1 minus x squared generates alternating 1s. 1 over 1 minus x cubed generates a 1 every third space. 1 over 1 minus x to the 4 generates a 1 every fourth space. And let's just consider this. And let's write this out. So if we were to write out what these generating functions look like, I'd have 1 plus x squared plus dot dot dot. 1 plus x squared plus x to the 4th plus dot dot dot. 1 plus x cubed plus x to the 6th plus dot dot dot. 1 plus x to the 4th plus x to the 8th plus dot dot dot. Now let's look for what this product looks like if we multiply it out. Well, how many ways can I get just 1? Well, 1, and that's if I take the first part of each of these generating functions. How many ways can I get just x? There's only the one way to get x, which is out of this one. Everybody else has higher powers of x. Now, how many ways can I get x squared? Well, I could either get x squared from here times 1 times 1 times 1, or I could get x squared from here times 1. So this is 2x squared. How about x cubed? Well, I could either have 1 times x cubed. I could also have x times x squared. Or I could just get x cubed out of here and then 1, 1, 1. So there are 3 ways to get x cubed. And this is probably not so fascinating yet, but now let's look at the number of ways to get x to the 4th. Well, I could either have 1, 1, 1, and x to the 4th here. I could have a 1 here, x squared here, and x cubed here. Or I could have an x squared here, a 1 here, and x cubed here. So we're up to 3 ways now. I could also have a 1 here and x to the 4th here, a 1 and a 1. That's 4 ways. Or I could just get x to the 4th from here. So I've got 5 ways of getting x to the 4th. So let's analyze those. If I got my power of x to the 4th from this first term, I want to think of this as x to the 4th times 1 times 1 times 1. If I got x to the 4th here, then I want to think of this as getting 2 powers of 2 from the 2's, and I'd get a 1 here, a 1 here, and a 1 here. So this would be 1 times x to the 4th times 1 times 1. Here the order is the order of these 4 terms. What if I got x to the 3rd here, and I got x here? Well, that would be 1x, so an x from the 1's, 0 from the x squared from the second one, x cubed here, and nothing here. So this would be x times 1 times x cubed times 1. Or I could just get x to the fourth here and 1's everywhere else. This would be 1 times 1 times 1 times x to the fourth. And finally, what's this one? Well, this is when I get x squared from here and x squared from here, because I have two 1's and a single 2. So this is x squared times 1 times 1. So again, just to go back over this, if I'm only looking for p of 4, I can consider these four generating functions and look at the coefficient of x to the fourth. The coefficient of x to the fourth is going to correspond to the number of multisets of natural numbers summing to n. Again, a multiset is like a set, so order doesn't matter, except I do count multiplicities. So 2 plus 1 is not the same as 2 plus 1, but 2 plus 1 is the same as 1 plus 2 plus 1. Okay, so the order doesn't matter, but the number of times each element appears matters. So hopefully this reasoning like this will convince you that p of n has a generating function, which is just an infinite product of these, which is to say an index product as j goes from 0 to infinity of 1 over 1 minus x to the j. So this pi means product. So if sigma was sum, pi means product. We're going to just keep multiplying these things together. All right, so we've got now a generating function for p of n. Let me put that down. So generating function for p of n is this infinite product. Product as j goes from 1 to infinity. Oh yeah, I said 0. Multiplying by a factor of 1 over 1 minus 0 is not a good idea. 1 over 1 minus 1 is not a good idea. That's dividing by 0. So I should have had an infinite product as j goes from 1 to infinity of 1 over 1 minus x to the j. All right. So now let's go back to this. Let's go back to this and count how many times we had distinct numbers. So here we had distinct numbers, here we had distinct numbers, here we did not have distinct numbers, and for the rest of these we did not have distinct numbers. Now let's count how many times we had all odd parts. We had all odd parts here, and we had all odd parts here. So there were 2 that had distinct members and 2 that had all odd members. Okay, maybe that's a coincidence, maybe not. Let's do the same thing for 5. Let's look at n equals 5. I've got 5. I could write it as 4 plus 1. I could write it as 3 plus 2. I could write it as 3 plus 1 plus 1. I could write it as 2 plus 2 plus 1. I could write it as 2 plus 1 plus 1 plus 1. And finally, I could write it as 1 plus 1 plus 1 plus 1 plus 1. And now let's check, are these distinct? And are these odd? So these are distinct and they are odd. They are distinct, they are not both odd. They are distinct, they are not both odd. They are distinct, they are all odd. Oh, no, they are not distinct, they are all odd. They are not distinct, they are not all odd. They are not distinct, they are not all odd. They are not distinct, but they are all odd. Again, 3 yeses, 4 nos, 3 yeses, 4 nos. Is this a coincidence? Of course it isn't. Let's figure out what we're doing here. Let's let d of n denote the number of partitions into distinct parts. And let's let O of n denote the number of partitions into odd parts. Well, theorem. D of n equals O of n. And no, it's not just poor handwriting. This will hold. And how do we prove this? Well, this might be difficult to enumerate these if we just try to make diagrams like this all day. But one thing we can do is come up with a generating function for each of these. So let's first find a generating function for d of n. So for d of n, I want to make sure that the coefficient of x to the n is the number of ways to write n as a sum of distinct terms. So to see that, we're going to set up our generating function as 1 plus x times 1 plus x squared times 1 plus x cubed times ... which is just the infinite product as j goes from 1 to infinity of 1 plus x to the j. And why should you believe this? If we go back to think about the child that could only get, say, 1, 2, or 3 apples, what we're saying here is that we can either, from the 1s, we can contribute 0 or 1. From the 2s, we can contribute either 0 or 1. From the 3s, we can contribute either 0 or 3, as opposed to before, where like the 1s could contribute 0, 1, 2, 3, 4, anything. The 2s could contribute 0, 2, 4. The 3s could contribute 0, 3, 6. The 4s could contribute 0, 4, 8, etc. So we're taking that same strategy, and this is our generating function for d of n. And if you're not sure, let's just compute again let's compute the coefficient of, say, x to the 4th. So the coefficient of x to the 4th, how do we get to x to the 4th? Well, we're going to either have 1, 1, 1, 4, or we'll have 0, 0, 0, 4, or we'll have 1, 0, 3, 0, or, so the number of ways to get 4 written distinctly should just be those ways, right? The number of ways to get 5 distinctly, I guess because we have it on this page here. So if we had this product up to 5, going bigger than 5 is not going to affect the coefficient of x to the 5th. We're either going to get 1, 1, 1, 1, and 1 from x to the 5th, corresponding to this, or we'll get x here, a 1, and an x to the 4th and a 1 to get this, or a 1, x squared, x cubed, a 1 to get this, and anything else is not going to be, that's all that this is going to give us for the exponent of x to the 5th. Okay, so this will give us when this is written as the sum as j goes from 0 to infinity of aj x to the j, these are aj is going to equal d of j. That's what I'm saying here. So you can work this out. Try this for some other natural numbers, and I think you can see how that works. So next, let's find the generating function for O of n. Well, O of n, we don't care if things overlap, but we do care that they're even. So recall the generating function for P of n was this, and this is anything goes. So what if I want P of n, but only to have odd parts? Well, the generating function for O of n, I'm going to call it g of x, and it's going to be a lot like the generating function for P of n, except it's an infinite product, j goes from 1 to infinity, and I only want the odd things to show up. So 1 over 1 minus x to the 2j minus 1. So here I'm going to make sure this is like the generating function for P of n, but I only get odd exponents. So the crux of this proof is going to be to show that f of x equals g of x. So let's write down f of x. F of x is, of course, this infinite product as j goes from 1 to infinity of 1 plus x to the j. And I can write this as infinite product j goes from 1 to infinity, of 1 minus x to the 2j over 1 minus x to the j. So what's going on here? This is just a binomial squared. To see this step, notice that 1 minus x to the 2n is always equal to 1 minus x to the n times 1 plus x to the n. It's just a binomial square. Okay, that's what's happening here. So this is a product of factors. I can split the product up to where I have the product as j goes from 1 to infinity of the numerator, 1 minus x to the 2j, over the product as j goes from 1 to infinity of 1 minus x to the j. And what is this? This is every possible exponent of j. Let's leave the top alone. Product as j goes from 1 to infinity of 1 minus x to the 2j. And let's factor the bottom part into even parts and odd parts. So I'm going to write this as the sum as j goes from 1 to infinity of 1 minus x to the 2j, these are going to be the even parts, times the product as j goes from 1 to infinity of 1 minus x to the 2j minus 1. So these two together, let's start here. I get 1 minus x. Well, 1 minus x comes from here when j equals 1. The next factor here is 1 minus x squared. That comes from here when j equals 1. Next factor here is 1 minus x cubed. That comes when j equals 2 here. 1 minus x to the 4th comes from when j equals 2 here. So these alternate back and forth, and you can probably see what's going to happen. Now I can cancel the top and the bottom, and I get exactly this infinite product, 1 over x to the 2j minus 1, which is g of x. So we just showed that d of n has the same generating function as O of n, which means d of n equals O of n, as we claimed.